We get to start our new unit today on electromagnetic radiation. What is electromagnetic radiation? Well, electromagnetic radiation, first of all, I'll tell you, is a wave. It's a wave that carries energy, just like any other wave carries energy. That's what waves do, is they carry energy. But it's not like the waves, in some ways, that we dealt with in Physics 20. Electromagnetic radiation is a wave that is energy. It doesn't just carry energy, it is energy. It's energy, pure energy, in a wave-like form. Pure energy that can transfer through nothingness, unlike the mechanical waves that we looked at in Physics 20 that needed a medium like air or slinky or water to carry themselves in. Okay, you jump into a swimming pool, somebody else on the other side of the swimming pool ends up feeling the wave a couple seconds later as a result of you jumping into the pool. Energy has been carried from you to them through the water wave, but that needed the medium, that needed the water to carry that energy through. Electromagnetic radiation is pure energy. It's energy in a wave-like form, but it doesn't need a medium. Electromagnetic radiation travels through space to us, okay, without the need to have something in between wherever it was produced and us. Now, what does it consist of? Okay, what does it consist of specifically? We say it's energy. Okay, that's kind of a loose definition. Okay, what do I mean by energy in a wave-like form? Well, it actually consists of two waves. Now, this diagram hopefully is going to make sense to you. It consists of two waves on two axes. There's an electric field wave on one axis, and then perpendicular to that, but in phase with that. In other words, when I say in phase with that, I mean when there's a crest of one wave, there's a crest of another wave. Perpendicular to that and in phase with that is a magnetic field wave. So you can see here on the y-axis, I have the electric field drawn as a sinusoidal wave, okay, a sine wave, right? Like what we picture a water wave as, right? Except this is not a mechanical wave, it's just an electromagnetic wave, but it's what we see a water wave as, right, as a sine wave. But perpendicular to that on the z-axis and in phase with that, we see a magnetic field wave. So if you look at my hands up here, okay, I'm going to try to demonstrate this for you if you can't visualize it here. Okay, my left hand is going to be the electric field on the y-axis. Okay, you can see what it's doing right now. Okay, it's following the sine wave on the y-axis. My right hand is going to be the magnetic field wave on the z-axis, which is this axis right here. And it's going to look like this, right? It's still a sine wave, but it's on the z-axis instead of the electric field being on the y-axis like this. So what this really looks like isn't like this. Okay, this is just, okay, an electric field wave. That's not good enough to have electromagnetic radiation. This is just the magnetic field wave. That's not good enough. What we need is both of those together, 90 degrees to each other like this and in phase with each other. So what the wave is going to look like is something like this. Okay, now this is really hard to do. Okay, trust me. Okay, this is like, you know, that thing where you try to pat your head and rub your belly and jump up and down or something at the same time. Okay, try it if you don't believe me. Okay. Electric field, magnetic field. Okay, you got both of these waves, both sine waves going on two different axes at the same time. See what I'm trying to do here? Okay, you see that? It took years of practice to master that, trust me. But we have both of those waves at the same time, but perpendicular to each other, both sine waves, both crests and troughs in phase with each other. All right, that's what an electromagnetic wave is. Now, direction of propagation, people ask me what that word means sometimes. Propagation, movement, the direction of movement of the wave. Which way is it moving? Well, if we have one of these waves, sine waves on the y-axis and one on the z-axis, the wave is going to move on the x-axis, right? Y, z, and x-axis, on the positive x-axis or the negative x-axis. In other words, if one wave is on one axis, one wave is on another axis, the movement has to be on the third axis. Everything's got to be perpendicular. Okay, one wave, 90 degrees to that wave is another wave, 90 degrees to both of those is the direction of movement. So one wave is on the y, one wave is on the z, The movement has got to be on the x-axis. Doesn't mean you can't flip things around a little bit, right? Maybe you got one wave on the x-axis, one wave on the z-axis. It's going to move on the y-axis like this. Okay, maybe you've got one wave on the z-axis, sorry, on the y-axis, one on the x-axis. It's going to move on the z-axis like this. So it's always going to move perpendicular to both of those waves. Does that kind of make a little bit of sense? All right. All right. So where does this come from? Where does this come from? Well, a guy named James Clerk Maxwell, Scottishman, not a lot of famous Scottish physicists, but this guy is one of them, suggested that a changing magnetic field produces a changing electric field. This wasn't new, okay, at the time. The idea that a magnetic field can produce an electric field if it was changing. Remember we said in our last unit, one of the last things that we talked about, that there's three ways an electric current can be produced by a magnetic field. You got a magnetic field that's moving, you got a wire that's moving, or you got a magnetic field that's changing in magnitude. If the magnetic field is changing in magnitude, it's going to produce a changing electric current, which produces a changing electric field. So you got a changing magnetic field ultimately producing a changing electric field. Okay, that's important. It's got to be changing, right? If it's just a constant magnetic field, it doesn't produce an electric field. But if you get a changing magnetic field, that's going to produce a changing electric field. Now, he hypothesized by symmetry, and we've talked about this before, about how physics is a pretty symmetrical subject, a pretty symmetrical discipline. When A causes B, B will often cause A. If a changing magnetic field will produce a changing electric field, then maybe a changing electric field will produce a changing magnetic field. So here's what's happening. You have an accelerating charged particle. That's what ultimately produces all this, is an accelerating charged particle, not a stationary charged particle. A stationary charged particle produces a gravitational field because it has mass and an electric field. Not a moving charged particle. Okay, a moving charged particle produces a gravitational field, an electric field, and a magnetic field. But an accelerating charged particle, okay, that produces a gravitational field, a changing electric field, a changing magnetic field, which of course produces electromagnetic radiation. Accelerating charged particles. Now what happens with this accelerating charged particle is that it generates this changing magnetic field and changing electric field. So it produces something like this. Okay, here's my, let's say, electric field, and here's my, on the other axis, my magnetic field. Now watch carefully what I'm about to do here. This electric field that's changing and this magnetic field that's changing were both produced by the accelerating charge. This electric field that we had will produce a changing magnetic field. So this caused this to happen. This changing magnetic field that we had causes this. So a changing electric field, we'll call it E1, produced a changing magnetic field that we'll call B2. And this changing magnetic field that we had that we'll call B1 produces a changing electric field that we'll call E2. Does that make a little bit of sense? But now remember, these guys are gone. We can't create energy from nothing. So as E1 produced B2, E1's gone. The energy from it is now in the form of a magnetic field, B2. And as B1 produced E2, B1 is gone because the energy from it is now present in E2. Well, now we could say that B2, okay, magnetic field 2 produces electric field 3. An electric field 2 produces, this diagram's getting a little bit ugly here, but hopefully you see what I'm trying to do here. Magnetic field 2 produces, magnetic field 2 produces electric field 3. Electric field 2 produces magnetic field 3. Well, then the wave that E2 that produced B3 is now gone, and B2 that produced E3 is now gone. This is the way the wave moves, right? An accelerating charged particle produces an electric field like this, okay, like this, and a magnetic field like this, but then this produces this, and this produces this, and so on. So the wave isn't just sitting there where it was produced by the accelerating charge. The wave ends up moving over here as a result of this constant circular thing where magnetic fields produce electric fields and electric fields produce magnetic fields. Make a little bit of sense? What's important here is that things are changing. Okay, a moving charged particle at a constant speed generates an electric field and it generates a magnetic field, but it doesn't produce EMR because it's a constant electric and magnetic field that it produces. You need a changing electric and magnetic field for this to happen. So we need an accelerating charge to produce the changing electric and magnetic field, not just a moving electric charge. Okay, that was the last unit. Okay, that still generates an electric and a magnetic field, but it doesn't generate what we're talking about now, this electromagnetic radiation. So it produces all this stuff, and one produces, E produces B, and B produces E, and E produces B, and so on and so on and so on. And that's what causes this energy to transfer, to move from one place to the other. And when it does propagate or move or transfer from one place to the other, it does it really, really, really fast. In a vacuum or in air, pretty much the same speed. It's slightly slower in air than it is in a vacuum, but it's just about the same speed. It's 3 times 10 to the 8 meters per second. In 1 second, light of any kind, right? We saw that video to start off, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Any of those types of EMR will travel at this speed, 3 times 10 to the 8 meters per second. That's about 1 billion kilometers per hour. That's so fast that light, if light could travel, you could turn on a flashlight, let's say in Halifax, and have that light travel from Halifax to Victoria, and then reflect off of a mirror and go from Victoria to Halifax and reflect off of another mirror and keep bouncing back and forth between Halifax and Victoria. The light would make somewhere between 25 and 30 return trips from Halifax to Victoria and back to Halifax again, multiplied by 30 in 1 second. 30 return trips across the second biggest country in the world in 1 second. That's how fast light travels. Now, it can't really do that because, I mean, the Earth is curved so much, right? Okay, you shine a flashlight in Halifax, and even if it was so strong that it could go that far, it would end up going off into space, right? Because the Earth is curved, it would never actually reach Victoria. But let's say it was flat and the flashlight could travel that far, 30 return trips in one second. 1 billion kilometers in 1 hour light will travel. Gary? Yeah. So we said it's caused by accelerating charged particles, right? Not moving charged particles, because we know that stationary charged particles produce gravitational fields, electric fields. Moving charged particles at a constant speed produce gravitational, electric, and magnetic. Accelerating charged particles produce, of course, gravitational, electric, and magnetic. But the big deal with these ones is the electric and magnetic fields are changing because it's accelerating. And that causes this EM radiation, this energy, to move through empty space, potentially at least through empty space. It doesn't have to be through empty space, right? Okay, if we flip on the lights in this classroom, Electromagnetic radiation will travel through air, travels through the glass in the window, but it doesn't need the air or the glass like, say, sound does. It can travel through empty space, whereas mechanical waves can't. You end up getting lost in space and you yell, unless you have some kind of radio, nobody's going to hear you because sound doesn't travel through space, through empty space, but light does. The radio waves would travel back to your ship or your home planet, but your sound waves when you're yelling wouldn't. So a little bit more detail on what it is, right? It's a transverse wave. Remember in physics 20, transverse waves like this, longitudinal waves were those, it's like sound waves, where you have a series of compressions and rarefactions, we call them. You need a mechanical wave for a longitudinal wave to happen. Okay? Electromagnetic radiation is a transverse wave. It's what we usually think of as a wave, right? A water wave is a transverse wave, consisting of two sinusoidal waves, an electric field and a magnetic field that are perpendicular to each other and in phase with each other, meaning when you have a crest of one, you have a crest of another. Trough and trough go together. One's on the x-axis, one's on the y-axis. It's got to move on the z-axis because it moves perpendicular to both fields. If one's on the x and one's on the z, it's going to move on the y. If one's on the y and one's on the z, it's going to move on the x-axis, right? Three axes, one field on one field on the other, and it's going to move on the third axis. Picture I have drawn here is same picture as I already had drawn. So it's kind of a hard one to draw too, so don't feel like you got to draw it again. Electromagnetic radiation is a wave, at least with the way that we've described it so far. We'll talk about a situation where it's not necessarily a wave later on in the unit. But for now, we're saying it's a wave, and we know that it's a wave because it exhibits certain properties of a wave. Three of these properties we've seen before in physics 20. Diffraction. Okay, let's deal with diffraction first. I should have listed polarization last because that's the one you don't actually know what it means yet here. Diffraction, that's the spreading out of a wave, right? If you have an opening like this, and a wave encounters that opening like this, it goes through the opening and spreads out like this. Okay, that's diffraction. Well, you know what? Light will diffract when it passes through an opening, and since diffraction is a property of waves, then light must be a wave, right? If it exhibits a property of a wave like diffraction, then it must be a wave. Interference. You guys learned about superposition principle last year. When a crest of a wave hits another crest of a wave, you produce a bigger crest, constructive interference. Or when a crest hits a trough, it produces destructive interference, or they cancel each other out. Remember that? Interference is a property of waves. And guess what? Light will produce interference. Light exhibits interference. That's a wave property, so light must be a wave. More support for Maxwell's wave theory of EMR. Refraction is the bending of light, or the bending of a wave. Not the spreading out like this, but the bending. Let me give you a little analogy here that if I taught you in physics 20, you've seen before. You got a boundary here between a parking lot and a swamp. This is the parking lot with pavement. And this is the swamp over here. And I don't know why exactly, but for whatever reason, you've got soldiers in this parking lot, and they're marching. If you're looking at them from above, from a helicopter, then it kind of looks like a wave front. There's enough soldiers, they're close enough together, it kind of looks like the front of a wave. And they're marching like this. Okay, they're marching up this way. So a couple of seconds after we're looking at them right now, maybe these soldiers are in different positions. They're all kind of marching at the same pace, right? Because that's what soldiers do. These four guys are keeping pace with each other, but this guy, hey, slow down a little bit. He can't keep up. How come? He's in the swamp. You can't walk as fast in the swamp as these other four guys can in the pavement. He's like, wait up, you guys. I can't go that fast. But they don't. They don't wait up. So now if you're looking at this thing from above, it looks something like this. Okay, a couple seconds later, these two guys are up here, and all of a sudden now these other two guys right here are in the swamp as well. Wait up! Can't go that fast. But they don't. So the wave ends up looking like this. The wave was going straight up, but now because the speed of the wave changed, the direction of the wave also changed. That's called refraction, the bending of a wave when it goes from one medium to the other. It happens because the speed changes. The wave either speeds up or slows down when it goes from one medium to another, and because the speed changes, the direction changes just like it did there. It's a property of waves. And electromagnetic radiation exhibits properties of, or exhibits refraction, so it must be a wave. This last one, polarization, that's new to you. You've heard that term before, but maybe in the context of sunglasses, polarized glasses or polarized sunglasses. Polarization is a phenomenon whereby you filter out all but a component of a light. If it's polarized horizontally, then you only allow the horizontal component of a light to go through, or of a wave to go through. If it's polarized vertically, it only allows the vertical component to go through. Let's say we have a piece of plywood here, a big piece of 4x8 plywood. In the middle of that plywood, we get this, this little slit, this little opening cut. And we got a rope that goes right through that opening. So going like this, right? Holding the rope up like this, going right through that opening. And I start flicking the rope vertically like this. Okay? So you get a wave like this, a sinusoidal wave like this, a vertical wave. What happens when it hits that opening? It doesn't go through. Right? This horizontal slit keeps the vertical wave from going through. Let's say I flick it like this so that it's going in a sine wave at an angle like this. What happens? Well, a little bit of the wave goes through. The x component of the wave goes through, but the y component gets canceled out, okay? Disappears there. If I fling the rope like this, horizontally, then all of it goes through because it's all x component. We would say that that wave is polarized horizontally. We're allowing only the horizontal component to go through. That make sense? That's that polarization where we filter out all the components but one is a property of waves. But it's exhibited by EMR. It's exhibited by light. So that must mean that light's a wave. Right? More evidence to support this wave nature of light, or of EMR in general. One final thing that I want to end off with today, and that's the spectrum. We're going to end off the same way as we started. Okay, the song was the electromagnetic spectrum, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. I'm going to teach you about that now, beyond what you heard in the song at the beginning of class. There are 7 general categories of electromagnetic radiation. The definition between each category is somewhat arbitrary, and these 7 types of EMR, understand that they're on a continuous spectrum. What I mean by that is that it's not like radio waves are exactly this, and then microwaves are exactly this. There's a range of frequencies of radio waves and a range of frequencies of microwaves, and in fact, there's even some overlap. There's even some overlap, okay, at the edges. Sometimes a wave can be of a certain frequency can be considered a radio wave. Sometimes it's considered a microwave. So it's continuous. It's not discrete. The types are ranging from low frequency to high frequency, or low energy to high energy, or in terms of wavelength, it's the other way around actually, high wavelength to low wavelength. They are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. want to tell you two things about each of these types of EMR. Number one, specifically how they're produced. Generally, it's by accelerating charges, but the specific mechanism by which each of these is produced. And secondly, the frequency range. Like what frequency are we looking at for visible light and so on. We're going to say that radio waves and microwaves are produced by oscillating electric charge. What do I mean by that? I mean electric charge is going back and forth, back and forth, back and forth. That's what happens in the wall of your house and in the wall of the school right now. And the wires inside the wall of your house and school, there's electrons that are alternating. It's what we call AC current, alternating current. They're going back and forth, back and forth, back and forth. If this is an electron, it has to speed up, reaches its peak speed, it slows down, it stops. And then it reverses direction, speeds up, reaches peak speed, slows down, and stops. It keeps doing that from here to here and back again 60 times per second. And as it does that, it has to accelerate. And as the electron accelerates 60 times per second back and forth like that, it generates electromagnetic radiation. Oscillating electric charge, charge that's moving back and forth, back and forth, back and forth, produces radio waves or microwaves. Infrared, Rich, you ever have trouble remembering exactly where infrared goes? Okay, remember that visible light is Roy G. Biv, right? You learned that in elementary school, right? Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. Infrared, infra means below. Below, red. Ultra means above. Above, violet. So infrared, visible light, ultraviolet have to go together because infrared is below red and ultraviolet's above violet. All three of those types of EMR are produced by transitions of electrons in atoms. And we'll talk more in detail about that in our next unit. But bottom line is, electrons are on one level, they fall to a lower level. As they do that, they give off one of these three types of EMR, infrared, visible light, or ultraviolet. Occasionally, by the way, X-rays can be in that category as well, but usually it's the first three. You'd have to have one really, really big transition to have an X-ray produced there, but it can happen. X-rays are usually, occasionally they can be produced by these transitions of electrons, but usually they're produced by rapidly decelerating electrons. So electrons that are going really, really, really fast and then come to a really, really, really fast stop. Okay, they have to decelerate so quickly, their kinetic energy has to go somewhere, and it ends up getting converted to an X-ray. You go to your dentist's office, and the dentist gives you an X-ray for your teeth. They have an X-ray tube that accelerates the electrons to incredibly high speeds and then smashes them against a metal target. And as they stop really, really quickly, they generate X-rays, which are focused through your mouth and get reflected off your teeth. You produce an image on a screen. Finally, gamma rays. Gamma rays are produced by nuclear decay. Or you could say radioactive decay. When nuclear decay occurs, matter is being converted to energy, and that's a little weird, right? You get energy from nothing. Well, not really from nothing, but it seems to be from nothing. The energy is coming from matter. Mass is no longer mass. Mass is converted to energy in that process. Now, the last property of each of these that I want to talk about comes with some good news and some bad news. What do you want first, the good news or the bad news? Good news or bad news? Victoria, what do you want first? The bad news, all right, Victoria, here's the bad news. Each of these types of radiation, all 7 types, has a range of frequencies. Each of these 7 types has a range of wavelengths. Each of these 7 types has a range of energies. We have to know all of them. So there's 21 different ranges of numbers that we have to know. That's the bad news. If you're anything like me, you have no hope of memorizing all 21 of those. I don't. Hey, ask me right now, I don't have them memorized right now. Okay, that's the bad news. But we got to know them. The good news is, ready for the good news, Victoria? Okay, the good news is there's a little trick that allows us to remember 3 frequencies and then figure out the other 18 from those 3. So you still got to memorize something, but it's only 3 ranges instead of 21 ranges. The other 18 we can figure out from it. Here's what I want you to do. Okay, I want everybody to memorize the frequency range of microwaves, of visible light, and X-rays, and then we're going to figure out the rest of them from that, or at least we can figure out the rest of them from that. The frequency range of microwaves is 10 to the 9 to 10 to the 12 hertz. So 6.2 times 10 to the 11 hertz would be a microwave. 9.2 times 10 to the 9 hertz would be a microwave. 3 times 10 to the 12 hertz would be a microwave. Visible light ranges from 4.5 times 10 to the 7, sorry, times 10 to the 14, I should say, to 7 times 10 to the 14. So we got to be a little bit more specific with visible light. Sorry, I should have said 4 to 7.5, not 4.5 to 7. Got to be a little bit more specific here, but that's okay because there's only 3 ranges we got to remember, right? 4 to 7.5 times 10 to the 14 hertz. In X-rays, 10 to the 17 to 10 to the 20 hertz. If you're given a frequency and you're asked to identify what kind of EMR it is, how to figure out what it is? Well, if it's in one of those 3 ranges, easy, right? I give you a frequency that's 6.9 times 10 to the 18 hertz. What is it? Jordan, what is it? 6.9 times 10 to the 18 hertz. What is it? 6.9 times 10 to the 18 is X-rays, right? Falls in that X-ray range, right? Because it's smack in the middle there of 10 to the 17 to 10 to the 20. Dickie, if I give you a frequency that's 6 times 10 to the 14 hertz, what is it? Times 10 to the 14. Good. It's going to be visible light. If I give you a frequency, Dylan, that's 3.9 times 10 to the 11 hertz, what is it? Good. Victoria, if I give you a frequency that's 9.1 times 10 to the 22 hertz, what is it? Good. Listen, we didn't have to memorize the range of gamma rays, right? Because if we know that X-rays only go to 10 to the 20, and we get, what did I say, 10 to the 22? Then we know it's got to be gamma rays. What if I give you one aurora that is 6.8 times 10 to the 13 hertz? What is it? 6.8 times 10 to the 13, sorry? Infrared, right? We didn't have to memorize the range of infrared because we memorized microwaves and visible light. It's got to be in between, right? So memorize those 3 ranges, and that tells you that any frequency can be found by either looking at the ranges that we have or in between the ranges that we have. Wavelength, you're given a certain wavelength. Let's say I'm given a wavelength of 6.5 times 10 to the negative 7 meters. What kind of EMR is that? Well, here's what I want you to do. You know, from physics 20, the wave equation says V is equal to F times lambda. Solve for frequency, V over lambda. V, if you remember, all of these types of EMR move at 3 times 10 to the 8 meters per second in a vacuum. The wavelength, let's make it 6 times 10 to the negative 7 for easier math here. The wavelength is 6 times 10 to the minus 7. That gives me a frequency of 5 times 10 to the 14 hertz. What kind of EMR is it? Austin, what kind of EMR is that? 5 times 10 to the 14 hertz. Visible light. So we didn't know, we had no idea what 6 times 10 to the minus 7 meters was for wavelength, right? Calculate its frequency and then compare it to the frequency, the 3 frequency ranges that we memorized. You do something real similar with energy, but we're not going to learn the equation for energy until later on in this unit. So right now, you're just going to have to trust me that, yeah, you can find frequency from energy, therefore you don't have to memorize the energy ranges, but you're just not going to learn how to do it for a couple weeks here.